Welcome, everybody. My name is Professor Ian Rainey from the University of Sheffield. I'm the Director of the Transforming Foundation Industries Network Plus, and today we have a guest speaker, Begona Ferrari, in our Blue Skies Greener Future webinar series. Her talk is going to be Colloidal Processing, Routes to Save Energy and Resources. Just for those people who aren't sure what the Transforming Foundation Network Plus is, I think I'll give a little bit of background before Begona begins her presentation. So we've been around for about 2 years. Our remit is to interact with the foundation industries, which constitute metals, ceramics, glass, cement, paper, and chemicals, the basic building block industries of our society. I think you can view them as. We're an organization that obviously does webinars, but we do face-to-face meetings and we do a lot of interaction with industry. And we've also funded quite a lot of projects in the past, up to about 1.4 million, about 34 research projects, up to 6 months in length, which are currently in part ongoing. Some are completed over the 2-year period we've been running. And these projects are all built around key aspects of resource and energy efficiency within the foundation industries. And that's why we've invited Begona to speak today, because she has a special perspective on that topic from the point of view of colloidal processing. Just to introduce a few of the players within our network. There's myself here in this image, Professor Rainey, it's me, Ian Rainey. The Deputy Director of the Network Plus is Susan Bernal-Lopez from the University of Leeds. We have Bill Sampson, who is from Manchester, who's now the lead protagonist on a new grant called Economizer, which is linked to our network. We have Cameron Pladle-Pierce from Swansea University, who also leads the Sustain Metals Hub, which is heavily linked with us in various ways. And our independent industrial advisor, the chair of our committee for that, is Richard Leese, who is part of CRH, was previously Carbon Pure and the Minerals Processing Association. Today, Neil Lowry will be running the event in the background, and he's the network manager. And we also have to thank Debbie Froggatt for organizing all of this, and she's the marketing officer for the network. So just to go back to the main screen here, we're going to have a talk from Begona. I first met Begona in Portugal not too long ago, about 6 months ago maybe. And quite honestly, I felt that she had a perspective on colloidal processing for ceramics that I was quite taken by. I thought it was an exceptional understanding of the area. And I felt that it was incredibly important in the concept of resource and energy efficiency to distribute and disperse this information and this knowledge that Begona has to the wider community, mainly in ceramics, but I do think it applies to other industries as well, maybe cements and so on, glass if you're looking at slurry technology or anything like that. She has a fantastic background. She is a scientific researcher at the Ceramic and Glass Institute, or Institute of Ceramic and Glass, I think you say it that way around, Begona, which is run by the Spanish Research Council. She has a spin-out startup company, Colfeed, if that's correct, Begona, if I said that correctly.
Yeah.
Her research group is generically called Tailoring Through Colloidal Processing. She has been extremely successful in gaining, I suspect, many EU grants, but also Spanish government grants, I would think. I don't know the details of that, but I'm sure Begona could tell you. And she is the General Secretary of the Spanish Ceramic Society. And anybody who understands how ceramics technology and industry is distributed throughout Europe understands that Spain, Italy are the dominant 2 countries in that area. So this is quite a very big thing to be General Secretary of the Spanish Ceramic Society. And she's a member of the European Ceramic Society Council. I think I've embarrassed Begona enough.
Mm-hmm.
So I'm going to hand off to her and stop sharing my screen, and she will give you her presentation, after which there will be a question and answer, which I will chair. So thank you very much.
Okay, thank you very much, Ian. So I'm going to share the screen, right? So thank you very much, Ian, to invite me to be here today. And also I'm really happy to kind of explain things about colloidal processing, and also what is the important thing that we can do for the main subject that we are worried about, like safe energy and resources, right? Right now, of course, just my place of working is the Institute for Ceramic and Glass here in Madrid. You are all invited to come to see us, right? And also, like Ian says, I am the General Secretary of the Spanish Ceramic Society. I think this is a very important part of my CV, because the Spanish Ceramic Society gives me an idea of the market of the traditional ceramic in tiles and red ceramics, and also refractories. And also in my work in the Institute for Ceramic and Glass, I have the scope of the advanced ceramics, right? Or technical ceramics. Also, I want to tell you that in the Spanish Ceramic Society, we have the academic point of view. We are managing the journal that is in the first quartile of the impact factor, right? And also we have prizes, right? We have prizes for the innovation of companies, right? Specifically these companies that is in close to the sea in Spain, in the Valencia coast, right? And we give them awards for the innovation in the companies, right? And finally, a couple of years ago, we have the experience to build a spin-off of the group in 3D printing of functional colloidal materials, right? And I'm going to talk some things at the end of the conference today, right? So what we are going to talk about here? Well, we are going to talk about the main subject that we are worried is the energy and the decarbonization of very intensive, energetic intensive ceramic industry, right? We are really worried about the energy consumption, and also we are worried really because we are burning a gas, and we are worried really about the carbon footprint, right? And also companies are also worried about how to recycle the raw materials, right? To optimize the process and don't depend so much of the external countries in raw materials. So these 3 points are the main subject that everybody in the market is talking about in industrial marketing, right? But also all the scientists, I'm sure, think that ceramic has opportunity here in the energy market, right? Because we can develop, we can prototype those solid oxide electrolysis and also photoelectrolyzers, and we can manage functional surfaces in ceramic in a different way and for different temperatures of working, right? That polymers can achieve, right? So this is an extraordinary opportunity for the ceramic, advanced ceramic and technical ceramic producers, the energy market that we are involved in, right? And I am really happy to see that people like Ceramini in the European market is also thinking that ceramic can help to other industry to go green, right? So this is important. We can do a lot of things in the market right now to improve and achieve new goals, and also to achieve new challenges and took opportunities in the energy market, right? So my field of work is powder technology and how powder technology can work and help, right? I think that scientific people are really worried about how to improve sintering, right? Sintering is the more energetic part of the processing technology of ceramics, and we want everything, right? We want densified refractory ceramics like carbide, nitride, and borides. We want to avoid the transformation of crystallography of the glazes or bioceramic or photoactive materials. We want to profile from nanostructure, and we want to full densificate or optical, magnetic, and ferroelectric materials, right? We want everything, and people is thinking how to do it from the point of view of sintering, right? And for that, in period processing, we are working to apply pressure, magnetic field, electric fields, and microwaves to improve our mechanisms of sintering. But also we have another kind of answer, right? We can work in indirect processing with colloidal materials and technology, trying to pack better our materials and achieve higher density, green densities before to go to the sintering, right? And also another important thing is trying to shape better, right? To achieve new complex shaping that maybe 20 years ago we don't believe we can achieve right now. Okay, so the scientific challenge, I think, in colloidal material is try to produce massively nanoparticles and try to use them in a correct way, right? And provide from this structure mainly for properties, right? But also for sintering, right? Because it's decreasing some degrees in the furnace when we use nanoparticles. The sintering process is decreasing in temperature, right? And also another thing that is important for us is related with the carbon footprint is to use water in the place of other kind of solvents, right, in our processing. So we are constricted by the green chemistry rules, recycling, and also valorizing of residuals. So we want to work in this context, right? Developing technology for shaping materials, for shaping ceramics. What is the main problem? Well, the main problem is that nanos have a huge specific surface areas, and we need to manage a lot of particles, right? When we talk about nanos, right? And most of the time in ceramic, we are talking about nanos, right? And also in functional ceramics, we have this kind of a structure, nanostructure, that it's really nice fashion, but it's quite complicated to manage then in powder technology, in dry, and even in humid, right? In wet technologies. So this is the challenge, right? The challenge in our case is how to manage an ink, right? How to prepare the better ink to shape materials, right? Really, ink is the word that we use right now because we are all talking about additive manufacturing, but depending on the area of research, we have been talking about slurry in industrial technology, or microfluid or suspension in another scientific disciplines, right? But at the end, the thing is how to isolate particles in a liquid, right? How to maintain stable these particles in water. This is the main challenge we can achieve, right? So the first thing that we need to think is about the chemical stability of the particles. For example, when we are talking about non-oxide or metal, or even when we talk about trioxide or multi-oxide ceramics, right? We need to passivate the particles. We need to know how the particles is keeping in water the chemistry, right? For example, it's very important for metal, of course, and very important for non-oxide, but also in trioxide, We need to avoid the lixiviation of cation, because if not, at the end of the process, we are going to lose the properties of our functional material, right? And also, we need to talk about the surface modification. We have polymer stabilizer that we can use to cover or change the surface of our particle and achieve the colloidal stability we need to isolate particle and disperse them in the water, right? This is a very important thing, and the tool that we use for that is the zeta potential, right? Studying the zeta potential of our suspension or particles in water, we can manage how we absorb this polymer, and also how this polymer is structured, and the stereochemistry of the polymer is going to influence us in our packing process, right? In fact, we need to develop, or we need to define, what is the hydrodynamic diameter of a particle inside of the suspension. This colloidal chemistry that we study here is influencing a lot how the suspension or the ink is behaving in rheology, right? In the rheology test, and also in the way we pack and the process we use, right? So if we measure the viscosity with the CR rate, having the same particle, independent of the kind of stabilizer we use, we have completely different rheology in our suspension, right? We can use the rheology models, Casson and Cross, for example, to calculate the main parameter of this rheology, of these flow curves. For example, we need to know how is the viscosity at rest, because with that we have an idea if we can storage the particles, avoiding settling or sedimentation of particles, right? We need to know what is the rheology in use, because with this number we can speculate with the possibility of shaping this ink, right? And also we need to know what is the rheology with infinite CR rate, because with that we have the idea how this suspension is going to react to a strong process like milling or spraying, right? So the rheology gives us an idea of all the process that we need to know, the parameters of the process that we need to know to shape a ink, to shape a material, right? So this hydrodynamic diameter is going to influence in packing. In fact, we can measure the viscosity as a function of the solid content in our suspension, right? And we can speculate depending on the hydrodynamic, how evolved the rheology. And we can, with the model of packing like this one of the Krieger Daugherty, we can measure the maximum packing density that we can achieve with this suspension, right? So for example, if you have a huge hydrodynamic diameter, we are going to achieve a lower green density in our 3D piece if we are using another kind of stereochemistry of the polymer that is absorbing the particle, right? Imagine that this is a very good idea, right? Because it's quite complicated if you are losing a lot of time to shape your material and measure the green density of the materials, and only measuring the viscosity we can have an idea how you are developing a good suspension to improve your process, right? Without shape any piece, ceramic piece, right? So this is an important thing to highlight of colloidal processing, right? The rheology gives us an idea how we can, for example, granulate, and we can have this dense granule inside, this dense structure inside of granules, right? Or material. So when we prepare a suspension, the fifth thing we need to know is how to stabilize the ceramic powder, okay, and isolate the particles, and also how we can dissolve or structural or polymer to make the structure of the material and combine them and mix them in a wet way to granulate this ink or to shape this ink or suspension, right? This is the way to work, okay? So if we go to granulation, right now we can granulate any kind of a structure we want, right? This is a very nice review of different kind of material that we can granulate using suspension, right? In a different way. Regularly, when we talk about shaping ceramic, we use this kind of granules, right? Material in the same side or different side, putting together to achieve a dense granules that you have here, right? These dense granules allows us to mix whatever kind of powder, right? We can mix ceramic, metal, polymers in different size and morphology. And at the end, we can have granules with different size, morphology, and composition. And this is a very good thing because we can transform a small powder in huge powder, right? We can, for example, avoid problems of fluency of this powder when we press, right? So this is a thing that the traditional ceramic is doing all the time, right? So they have, in fact, a lot of experience doing that. And right now, we are using this kind of industrial processes to manage a mixture between ceramic and metal, for example, in soap technology materials like hard metal, right, where we are mixing the non-oxides with a metallic matrix, right, and we achieve this kind of structure here. And you can see that this sintering is so good that is the ceramic that is broken in the place to break the joining in between the metals and ceramic, right? So this is an important thing to granulate the materials, to use this kind of granules and avoid fluency problems in our material. I told you that, of course, this is an industrial process, right? That, for example, but people, for example, in the companies of polymetallurgic don't use at all, but they need to introduce it, right? Because the mixture in wet is very good, is better than drying, right? That in dry way, right? But if the companies in ceramic know how to do that, why we can help them, right? What we can do next, right? So the first thing that the science can help the companies is avoid trial and error work, because this is time consuming, right? And we need to use the predictive analysis, and this means that we are earning time, energy, and money at the end, right? So if you see the porcelain diagram, right? One thing right now in the traditional ceramic companies is how to have the correct raw materials, because this material that they use that regularly is taking place is changing and affecting the sintering condition, right? So how we can go to see colloidally if this raw material is working good for us or not. Well, mixing condition, of course, is affecting to the thermal reactivity, to the consolidation process, and of course of the mechanical properties of the 3D parts, right? And this is the part of the process of mixing that is really sensible to the influence in the final properties of the material. We can measure currently the particle size right now, even in the companies, without any kind of problem, right? But if we use this diagram and that I told you on the modeling of packing, we can choose in the first place the stabilizer that we can use in in the shaping, right? In the preparing the stable suspension. In this case, as you can see here, we measure the viscosity with the volumetric fraction of the feldspar slurry, right? Using different kind of chemicals, right? And we are ready here to say that if we use this chemical, we are going to have a better suspension, right? And for example, if we are going to examine different kind of powder, in this case, different kind of kaolins that have more or less the same specific surface, so we can, and more or less the same particle size, so we cannot say what kind of kaolin is better or not. We can go to the rheology, right? And we can fit our suspension or dispersive suspension of kaolins, right, with the rheology of the mixture, right? And you can see here that all the suspension of kaolin is fitting the rheology of the mixture. But in this case, if you can see, we have one of the curves is going up, and this kaolin, for example, is changing completely the rheology. Can change the rheology of the mixture, right? And this one is have a good rheology behavior. So if I saw this rheology diagrams here, for sure I'm going to choose this kaolin and this kaolin to take them to improve our mixture to make the porcelain, right? So the rheology here is a tool to choose raw materials, right? And this is one of the important things that can offer the colloidal chemistry and the study of the rheology and see the potential of the material, right? And if we talk about shaping at the end of the project of the process, I mean, when we want to shape finally our piece, right? We have many kinds of ways to shape our suspension, right? And recently, the more used one are these that we call near-net shaping technologies, right? Where we use gel agents, or when we use a shaping process that gives us the final shape of the material, of the ceramic material, right? All this shaping process, we use many kinds of polymers there, right? We use polymer synthesis of powder, but also for shaping, right? Binders, plasticizer, for example, intake casting, or gels and thermoplastic, for example, for gelling, Egno and exotemplates to make porous or ceramic precursors, even in different kind of materials to improve rheology, right, and decrease the thermal treatment, right? All these materials we need to include in the slurries. And also we are worried about what kind of this material we can use, right? Because we need to meet the regular rules of plastic recycling, of using biomass, right, to decrease the carbon footprint of this process, right? So we can do that. That means we can use this kind of materials to improve all our material or shaping material, right? The answer is, of course, yes, right? This is, again, the case of a study of the sanitary porcelains using gels, right? You see here in this diagram that we have the mechanical properties, in this case, the fracture strength, with the evolution of different kind of pieces, with the solid concentration that we use in the suspension, right? So when we change the stabilizer and the solid content of the material, we are improving, we are in the same fracture strength, but we are using less amount of material in the suspension, having exactly the same fracture strength. And this is because we are using the right stabilizer, right? By the time that we change the inorganic composition, choosing very good the raw material, we can improve the structural strength, right? Without changing the solid fraction of the suspension. But when we use methyl cellulose inside of our suspension, and of course inside of our green material, we can increase the fracture strength, even decreasing the solid fraction. And if we use a better modifier, if we use the carboxymethyl cellulose like a structure of our suspension, we even can achieve a higher fracture strength with a very, very low amount of solid fraction in our suspension. So definitely using a stabilizer, changing or choosing a better raw material, and also using different kind of polymer like structures can give us a better fracture strength, earning also the amount of material what we are using to prepare the suspension or the slurry, right? So the stabilizer, the gels that we are using can help us in our process, right? And can improve the mechanical properties of our material. Here I can see, you can see different samples that we prepare in this test that I saw the results. And here you can see these sanitary devices, okay, that we prepare with this suspension with assisted or additive with these gels materials, right? So finally, we are using different kind of polymers to manage or to improve our properties, even industrially. And I want to talk, of course, right now at the end about the most, I think, successful process that we are dealing right now in this new revolution, industrial revolution, and is this one of the additive manufacturing, right? In fact, if you see here, most of the gelling or additive for polymerization, for help to shape our material, we use also here in additive manufacturing. The other thing that changes here, we can prototype the material, we can shape different kind and complex structure added by the technology of CAD, right? So we have many processes in additive manufacturing. We have this kind of powder bed process, like, for example, the laser additive manufacturing that we are communicated at a strong energy or powder to shape, focus energy of powder to shape of our material. This kind of structure of technology in ceramics can help us to create new material. You can see here in this micrograph a mixture between alumina and 40% of zirconia, and you can process it by a slip casting and also after sintering, right, in a regular treatment. And here you can see here what is this same composition, the microstructure you achieve when you use a laser sintering, right? This kind of direct powder bed sintering technology, right? So in this kind of additive manufacturing, we are creating new materials to study, right? We have also the binder jetting. The binder jetting is very interesting way to shape material, but we have quite different problem because the green density of this material is quite low, right? So we need to improve this technology, and definitely we need to granulate to improve fluency of our powder bed, right? To improve this kind of materials in this advanced manufacturing technology, right? And later we have this inks or filament processing, right? We have robocasting or direct writing that we use paste or inks. We need to stabilize and measure the rheology, and most of the time we are using gelling agents, right? We have the fused filament fabrication where we need also stabilize our suspension and rheology, and we are using melting like to shape a melting process to shape the 3D piece. And we have the stereolithography or digital light processing. We are using here inks, and we need to cure this the resin we use to shape the ceramic. And we have this inkjet printing where we are using also inks, and most of the time this technology is to use to draw a pattern in a surface, so we need to know a lot of wettability, right? So focus in this last one, that is I think the most industrialized process, additive manufacturing process. We can see that in material jetting we're using an electric field to create a goat, right? To create oh, it's not working. Oh, okay. It's working, yeah. We need to, we have a piezo element inside of the head of the printer, right? And we are communicated to the suspension in movement, right? And we are creating different goats in the head of the printer, right? And we are able to draw to make a pattern in the top of substrate, right? This technology is really, really industrialized. In fact, all the tiles that we have at home right now are made by this technology, are designed with this technology. We can replicate marble, we can replicate any kind of design that we want by material jetting in our tiles, right? And also is starting to be used in functional materials to create different kind of photo catalyzers in the top of glass, and also to build these photocellular devices in the top of the tiles of the roof in our houses. And of course we think that we can achieve this kind of material, this kind of to shape this kind of advanced material inside of our houses in different places in the house, right? Using this material jetting technology, right? And in science, the most important thing that we need to take care in the inks is to check the particle size, the surfactation of the ink, the viscosity and the density, to avoid the dry defects, right? And also we need to adjust the printer parameters, right? And finally, we can make our pattern. In this case, this is nano titania in a water suspension, right? And finally, you see here how you are going growing this kind of pattern layer by layer with really a good resolution, right? So this is an opportunity, of course, for ceramic producer to create this kind of things for functional material, not only for the structural ones, right? In construction wise. Another kind of technology can be the material extrusion. You know, we can extrude a paste, an ink, or a filament. If we are extruding a paste, is doing robocasting, right? You need a good equipment with a lot of pressure in your paste, right? If you are talking about direct writing, the requirements of the equipment is not so high, but you need to know a lot about the chemistry of the suspension of the ink, right? One thing that is quite complicated for gelling is to maintain the shape, right? The gel's structure is not so rigid that we expect, right, in ceramics. So I think that it's better to use thermoplastic for that, right? And change to the thermal extrusion and do fused filament fabrication to shape or ceramics, right? This is the company that we create in 2020, right? Based, of course, in a wet mixing, right, of the thermoplastic and the particles, and doing this kind of granules in our materials, mixing the plastic and the particles in, right? In this way, we are able to create this kind of filament. We are using a very short, a small extruder with only 15 centimeters of hot sun, and temperatures in this case of extrusion that is around 150, 170, right? And you see here how we can extrude our material or granules, and how we can create the filament and bobinate it, right? So this is the way that we work in the company, right? And in this material, we are able to put many kind of particles, magnesium, for example. And thanks to the zeta potential and rheology studies, we can isolate the particles inside of the polymeric matrix. You can see here all the particles alone in the polymeric matrix, and we can shape any kind of piece. And also we can engineer the equipment, but we can engineer the feedstock also, trying to avoid the closing of the nozzle, right? Creating links between the particles and the polymeric matrix, and study the rheology of this composite, thermoplastic composites, in using oscillatory test, because we are talking about extremely viscous fluid like a composed, thermoplastic composed melt, right? So we need to know more than the temperature of degradation or the temperature of melting. We need to know also how this thermoplastic is behaving, right, when you try to print them, right? So this is a part of the rheology, very interesting to study, because give us an idea how the matrix is working, and also how the particles interaction is effectively changing the fluidity of this melt, right? And also can give us an idea how we need to work, because if we change the deformation of this material, of course, is changing the behavior. In this case, for low deformation, we have a viscoelastic material, but here with higher deformation, most of the time we have a solid material, so we cannot print them, right? And finally, we can describe also the rheology of this melt and give us an idea how we can extrude and how we can print or thermoplastic materials, right? We can put many kinds of things inside, right? This is an example of graphite and graphene. You can see here the particles. You can see here how we can organize these particles inside of the filament, right? And with that, we can manage the conductivity of this small filament, achieving even with a very low amount, 25 volume% of carbonaceous species inside of the filament. We can achieve a 10 Siemens centimeter, meter, no centimeter, meter conductivity of our filament, right? We can print whatever shape we want. We are talking about the more cheaper machine in the world of the additive manufacturing, and also printing this material. We can change also the conductivity of our materials. We can design the porous structure, right? This is not cellular porosity. This is porosity designed by CAD, right, in a random way or in a linear way. We can change the material, use nanotitanium, and we can also make many kinds of things. This is the case, or a photoactive composite to use for cleaning water, right? You can see here that we are able even to perform porous filament, right? That increase a lot the photo degradation of the dye. In this case, for example, we are using hydroxyapatite inside of the material. You can see we can print regularly with a regular machines, desk machine of printing, right? Different kind of structure. You can see all the small hydroxyapatite particles surrounding by the plastic, right? This is the result of wet mixing. And of course, we can achieve a 50 volume % hydroxyapatite inside of our filament. And we can try to debind goods. That is not so easy sometimes. And sinter or material, right? This is the structure of it, full hydroxyapatite, right? So we can do that with hydroxyapatite, and we can achieve a very nice porous structure inside of the filament, and also very good joining between layers of the scaffold, right? After the thermal treatment. And we can do that, of course, also with another kind of ceramic particles like zirconia, for example. You see here that we have 45 volume % zirconia in our filament. That means that we have 40% of shrinkage after the thermal treatment and sintering, right? But the shrinkage is really good controlled and give us a very good dense material, right? Close to 98% of final density, right? So this is the way we can print the alumina filament in our printer, right? And we are achieving really, in this case, you can see here, we are achieving really structures of zirconia that maybe 20 years ago, we think that is completely impossible, right? To have this kind of shapes in zirconia, absolutely designed by digital technology, right? So this is, I think, is a huge step we have with additive manufacturing, right? This kind of material. Right now, this technology are developed for powder like this one here. We are working here with hard metals. In this case, is tungsten carbide with a little amount of nickel, right? Think about how the possibility we have here to manage and to design this kind of tools that is very technological tools, right? For additive manufacturing, using additive manufacturing, right? We need to put a lot of material inside of the thermoplastic matrix, so we cannot assure the flexibility of the filament, and we need to use powder in. This is why we are using this kind of equipment. And also we can manage and print multi-material. We can mix, for example, titanium graphene here, you can see, and we can achieve this kind of a structure inside of the filament, right? So mixing titanium and carbon inside of our material, sintered material, right? So this is also something to explore right now. So to finally make us resume of how the colloidal knowledge has been evolved during the last 10 years, right? We can start with the very well-known DLO theology, but if we advance to the suspension stability, to the processing of the suspension stability using the double layer repulsion, but just at the end of the 80s, we start to learn how to absorb the polymers and better stabilize the suspension. And of course, when the nanotechnology arrived, we have the possibility to see how these particles behaves together with the use or tools like the AFM or XPS analysis, right? And finally, we can describe perfectly how we can absorb the polymer, how we can organize this polymer in the top of the surface, and how this crystallography behaves in our suspension, and also how we can manage the absorption of particles. And definitely right now we are able to manage our surface, the surface of the solid, the polymers, the stereochemistry and the chemistry of the polymer. And this gives us an idea how we can pack these particles in suspension, right? How we can shape this suspension and what is the better suspension using only the viscosity like tool, right? And with that, we can create microparticles, granulates, nanocomposites, 2D additive manufacturing, 3D additive manufacturing, metal, ceramic structure, even near-net shaping structure. And this is, I think, the huge step to create these kind of materials in different places, right? In energy, in biomaterials, in structural biomimetic materials, right? And this is the challenge, right? How to use these particles inside of a suspension to shape this material in our machines, in our processing, right? So the last thing is, thanks to my group of research and the people of the company that is working really, really hard, all the project we have for funding this research, and all of you, of course, to thanks, listen to me during these minutes, and Ian, of course, to give me the opportunity to be here. So thank you very much for everything, right?
Thank you very much, Begona. I learned a little bit more this time, so that was marvelous. I learned everything. It takes me several times to get hold of things in my head. We have a couple of questions that have been coming through the chat, and I will open the talk generally up for questions as well. But I'll start with one from Peter. We have no second name or affiliation, so hello, Peter. He thanks you for the presentation, and he asks, when you showed the plot of fracture strength versus how do the stabilizers work to reduce solid fraction and at the same time increase fracture strength? And when you say fracture, under what kind of loading?
Yeah, I have not, I'm sorry, because I have not exactly the loading, right? But it's the green shapes, right? It's not the cinder shape, right? This company, in fact, was looking for how to improve the managing of the piece, right? Think about these huge pieces, right? That you really cannot manage very well in production, right? So gelling is giving the opportunity of people to manage this kind of pieces, to handle it very well, right? So they are looking for increase the fracture thickness of green size of green pieces, right? And of course, think about, you have a polymer there. That means you don't have only particles, right? You have polymer also, right? You have a networking of the gelling of the gel, the gelling agent surrounding the particles, right? So gel is giving you the toughness that the green ceramic piece has not, right? So this is why with lower amount of particles inside of the shape, you can manage very well this shape, because you, in the place to have particles, you have gel inside, right? So this is the thing, right? And gel is giving you the opportunity to manage very well this piece, right? And after that, region sintering gel is gone, right? The amount is not so huge. So you can define it very well, your piece, right?
Thank you.
Thank you. I hope that is useful, Peter. So if anybody wants to raise their hand or put something in the chat function, please do. The question I have, I mean, I've come at this from a quite different place than perhaps additive manufacturing. I guess I want to ask a rather leading question of Begona. In her experience of working with factories, how many do you think have an optimized process for granulation and for slip casting or for pressing based on colloidal chemistry? So do you think there's a big area of research to be done there? And I'm thinking mainly in the idea that you can reduce pressing flaws and therefore increase yield in any production. Do you think it's, if you went into your average factory, do you think there's improvements you could generally make? I don't want to say specific names, but that would be incredibly powerful if we could improve this pressing.
Of course, if you manage and optimize the suspension, you can improve your production, right? Something in the last year, something happens very funny to me, right? People working in polymetallurgy don't know nothing about spray drying of suspension. They usually atomize metal, right? So the shaping of these kind of granules that you have here, right? Oh, okay, this one, right? This one. You can press better, right? Because people in metal is looking to achieve the particle size that we are used regularly in ceramic, right? So we in ceramic we use 20 macrons, 30 macrons if we're talking about traditional, but nanometers if we are talking about technical ceramics, right? But people in metal is using 100 macrons or 200 macrons particles, right? This is why they press very well. But when they go to 10 microns, they cannot press at all, right? So if you make the suspension and granules working with granules with this one, you can press again. And at the end, you have a material that have a lower gran size, right? So it has better properties, right? So this market is is improving or profiting from suspension from 10 years ago, right? So of course we can improve the process if we mix better, right? We can manage nanos, we can manage and unpack better, right? And also we have all the rheology modifiers to give us a shape, right? So I think that colloidal materials has a very relevant step for processing, right? I don't know, Ian, if I answered your question.
Yes, more or less, yes. My experience of ceramics companies is that there is little investment at all in the slurry and colloidal processing and the granulation technology. It's usually something that they've had for tens, if not 20s and 30s of years. It hasn't changed. And the yields in production are not often that great, with many flaws emerging during the post-pressing or process. So you don't notice a flaw until you fire it, and then you have a big crack in your tile or your plate. And I suspect that one of the things that we should look at in detail if we want to work with factories to improve their resource efficiency is to minimize wastage by minimizing pressing flaws, by optimizing slurry processing. Would you say there is a reasonable perspective from your research that you've done?
Oh, of course, yes, because thinking that when you improve your granules, you have this kind of completely dense granules, right? You have no holes there, right? So you can pack better, right?
Yeah.
You know, my opinion in that is that traditional companies has people that has been working for a long time there, right? And they know better than my laser how the paste is working well, right? But right now, these people is going on retire, right? And we have right now tools to know or to optimize this slurries, right, in a better way. But it's quite complicated because, for example, if you improve the density and the composition of a sanitary porcelain, for example, you can decrease 50 degrees C or 100 degrees C your furnace. Yes, you can do that, but you should count with the company, right? Because moving the furnace is quite complicated for the company, right? I don't know if you have the same idea like me, right? When I arrived to the companies to work, the most complicated way to convince there is changing the temperature of the furnace.
Everything changes.
Yeah, it's quite complicated, sorry.
It's very difficult.
To convince them, right? This is the thing.
Yeah, it's very hard to get them to change anything because they have a product that
it's working well, right? So they need a huge advance, right?
My concern is, I guess my concern is depending on what you're making and the thickness of what you're making, there's quite a lot of wastage. That means that they have runs that don't work well, they have problems, and some of that will emerge because of the lack of understanding of the slurry and the granulation process. So I think it's an area where we can improve resource efficiency, and this is not insignificant. This is not 1% or 2% wastage. It can be as high as 30% wastage, so that you can, if you eliminated 10 or 15% of that wastage, you're massively improving the resource efficiency of that product and decreasing the embodied carbon. This is a very important area. And there are parts in the process which are super critical, one of which is going to be how the particles compact together during the pressing process for a tile or a plate or whatever you're doing. So I see this as technology that goes all the way from making a tile for a wall in a bathroom, all the way to 3D printing of the most complicated materials that you could really imagine. You've got phenomenal composites that are almost impossible to imagine to be made by any other way. And this is the strength of the work. It underpins just about every aspect of ceramics and ceramic-based composites.
Yeah.
So if there's no more questions for Begona, I think again a lot of thank yous, but we're out and we're now past the 1 hour, so I'm afraid the time is up. So thank you very much. I've enjoyed it immensely. Every time I listen to this, is the second time I've heard you speak, and I've learned a little bit more. And hopefully I'll hear you speak again someday, and I'll learn a little bit more again. But I certainly am going to, when I work with the companies in the UK, I'll be focusing a little bit more on the chemistry of the granulation process and of the pressing process.
Yeah, very important.
Yeah, I will be doing that a little bit more. Thank you very, very much. And I think if we just thank you, I don't know how that works because clapping gets a bit loud and a bit much. But so thank you very, very much.
Thanks a lot.
And thank you everybody for participating. It is, I think the talk will be available online in the fullness of time if anybody wants to capture a little bit more of the science that Begona has presented. So thank you very much, everybody.
Thank you.
Bye-bye.
Bye-bye.